All right, hello everyone, and welcome to today's webinar. Today's CFD Build Your IQ CFD webinar is Scalar Mixing Analysis, and this is going to be part one of a two-part webinar series. My name is Marwan and Amal, and I'm a technical support specialist with Autodesk, and with me is Amal. Go ahead, Amal.
Hi everyone. My name is Amal. I'm a technical support specialist supporting Autodesk CFD products, and I'm based in our office, Munich, in Germany.
And I'm in our Pittsburgh office.
Cool. Let's get started.
Yeah, just one thing here, which is at the bottom of the slide here. Today's webinar will be available for download at the link shown at the bottom of this slide.
Right.
So let's go ahead and get started. What we have here are a bunch of slides and followed by 3 example models. So today's content is going to be, of course, about mixing, general overview, steps for doing a mixing analysis, scalar analysis, material properties in a scalar analysis, and some example models. Mixing analysis, just a quick overview. In CFD, fluids are set to the same materials, since fluids with different properties cannot touch or interact with each other. So when we say mixing, of course, we have 2 different fluids that are going to be mixed together, but as we all know, CFD does not allow you to have 2 different materials and the fluids mix or touch each other. So we do that using Scalar. Scalar is used to distinguish different materials. Mixing can be done with the use of Scalar or without the use of Scalar, such as mixing same fluid with different temperatures. That's going to actually be the first example that Amal is going to show, is without using Scalar, just different temperatures. The other way is, of course, with using Scalar, and we're going to use Scalar to distinguish between the 2 different fluids, and we'll see how we do that. Mixing, of course, can also be done with mechanical agitation. We're going to not cover that this webinar. Probably in the next webinar we'll talk about mechanical agitation, such as motion to mix the 2 fluids.
Marwan, would you mind that I add something?
Sure.
Actually, I had some customers who were asking if it is possible to use scalar mixing analysis when simulating more than 2 fluids. Actually, this feature is only available for 2 fluids. We can only have scalar 0 and scalar 1. We can't have like scalar 3. Yeah.
No, and because if you have another fluid, let's say it comes in at scalar 0.5, they're all going to be mixed up together. It's going to be hard to know which is which. So,
actually, it's
yeah.
only supported with 2 fluids right now.
That's right.
What is next? What have you prepared?
All right, scalar analysis. The general steps for doing a scalar analysis is to specify scalar boundary conditions. So at the inlet of, or one of the inlets, you specify a scalar of 0 or 1 or anywhere in between. You specify a scalar initial condition if you are doing a transient analysis. You would activate the scalar in the solve dialog, as you can see here. So you go to the solve, physics, advanced, and you change it from no scalar to general scalar. And you enter the diffusion coefficient, which will define how the 2 fluids are mixing with each other. This can be left at 0 if they don't actually mix together. That's okay to do that, but if they're going to be mixing together, then you would want to set that to something different than 0. Next topic here on the slide is fluid properties. The fluid properties in a scalar analysis can be fixed or variable. If they are set to fixed, the fluid properties, basically none of the fluid properties will be a function of temperature or scalar. By the virtue of them being fixed, they are not a function of anything. They're just fixed. Scalar in this case is used to track the flow and mixing in the fluid domain. So you will be able to, display the scalar and see the coloration and see how one fluid is interacting with the other, even if the properties are fixed. Now, of course, you can set the properties to be variable. In that case, any of the fluid properties can be a function of scalar. Don't all have to be a function of scalar. One of them, let's say the density, can be a function of scalar. Something else can be a function of temperature or pressure, but it's up to you. You can make them all, or one of them, a function of scalar. You will set the variation method to something like piecewise linear. You will pick the scalar as a property, as what the property will be a function of, and you will fill the table of properties scalar. And I think on the next slide, maybe not. We'll show that in our example. One important thing here when we talk about variable fluid properties is the density. Realistically, and in many cases, density can be a function of both temperature and scalar. But in CFD, the density can only be a function of one or the other, temperature or scalar, not both of them at the same time. So what the user will do is they will set the density to be a function of the one that has the larger effect on it. So if scalar has a larger effect on density, then you will set the density as a function of scalar. And if temperature has a larger effect, then you would set the density to be a function of temperature and not scalar. So that is very important to note. Next, I'm going to pass this to Amal, and she will go through the example of a faucet. This is like an old-style faucet. Yeah. Go ahead, Amal.
Right. Thanks, Marwan, for the information. It was really interesting to know all these information about mixing analysis. Okay, actually, now we're gonna walk through some settings and results of very simple models that we run. For example, I chose this old-fashioned water tap so that to simulate the mixing of water, hot and cold water, not using scalar, but to show how density is changing with temperature, and how we can define it in the material properties. So here we have the inlet of the cold water, here we have the inlet of the hot water, and here we have the outlet. Okay,
Amal, did you take the presentation over? Because I don't see your screen at this point.
Okay, just a second. I should switch to presenter.
That's right. I'm gonna make you the presenter.
Okay.
And
show my screen.
You want to show your screen? There we go. Okay, now I think you have the PowerPoint presentation. Go ahead and bring up the model, please.
Okay, so do you see it right now?
We see this the slide, yes.
Okay, cool. So probably you didn't see my the mouse. So here we have the cold water, and here the hot water, and here the inlet, the outlet. Sorry. Actually, I got this CAD model from this website where you can find a lot of CAD models on which you can run CFD simulation too, like I did. So let's move. Here I wanted to show how we define the material. So this is the material editor. I created here a new water. I called it water temperature. And then I changed the density to vary according to the equation of state. So here the variation method equation of state. And I made sure that the material environment is set to variable in order to allow to the fluid properties to change. So let's move. Here are the results that I got. So we have here the temperature profile. As you see here, the cold water comes in and the hot water comes from the second inlet, and they mix with each other till the outlet. Here you can see the results or the effect of the temperature change over the density according to the equations of state. And then after analyzing my results, I noticed this. Oops. I noticed that the outlet or the flow over the outlet is non-uniform.
Amal, are you sharing the CFD screen? I'm not sure if everyone can see that.
You mean the software?
Yeah, the software.
Okay, probably it's better.
Yeah.
Here is it. So this is my model. And this is it.
Okay, we can see it now.
Cool, thanks Marwan. So here is it. And after that, I noticed that we have like a non-uniform flow over the outlet. And I said, so it was probably the reason why nowadays they changed the model of the mixer to a more developed one. Probably they are getting, I'm not sure, I didn't simulate the new mixer. You can do it, why not, and you can share with me the results of it. Probably for the new models, they are having more uniform flow, so more uniform temperature profile in here. So, and then for this, we got like a simple model, we got the results, and then I said, okay, for this, I checked everything, and then the results told me that this is not the good model. So probably I will let you the chance to simulate a new mixer and share with me the results you got about temperature, if it is uniform, if you got better results than this one that I have done. Second, we're gonna move to a second model in which the fluid properties are changed depending on the scalar, not on the temperature this time. So I have a simple tank here with two inlets. One inlet is getting or pushing water, and the second one is pushing methane. And here down it's the outlet. It's a very simple mixing tank. So for the material definition, we have, like usual, as usual, a new material. I call it mixer water methane, and then here I defined, I changed the density to vary according to a piecewise linear method, and then I made it depend on scalar. So you're gonna probably ask if it is important to change also the other properties. I will say it depends on your simulation. If you're also interesting to see the effect of changing the other properties according to scalar. For me, I tried both piecewise linear here, constant viscosity, and piecewise linear for density and piecewise linear for viscosity. I didn't see a big difference in the simulation results. So for this table, I got scalar 0 for water, so this is the density of water, and then scalar 1 for methane. And as usual, I made sure, as Marwan mentioned, that we set the material environment to variable. Now, let's move to setting the boundary conditions, how I have done. So over inlet 1, I have a mass flow and scalar 0 related to water, and then inlet 2, it's mass flow rate with scalar 1 related to methane, as I already mentioned. And at the outlet, I have pressure equal to 0. Then for the meshing, I would recommend that you suppress the solid parts as you're only interested in simulating or seeing the fluid flow. And the advantage in here is to make sure that you don't have a long run time when having a big mesh elements when meshing the solid parts. And I would recommend as a second thing is to use refinement mesh regions where you are where the flow or where you are interested in the flow. For example, the inflow and the outflow in here. For the solver settings, next to setting or saying that this is a steady state analysis, as we are in the steady state analysis, as already Marwan mentioned, have to set the general scalar of water and methane in this case of your two fluids that you are simulating. And as I told you, it's very important to create the mesh regions on the positions that are very important where you have a high gradient or a turbulence. So as you can see here, it's a coerced mesh that I've made, and this one it was when I created like a mesh region over here. It's a cylindrical one and a cylindrical one over here. And you can see how the refined mesh showed a very good fluid flow in comparison to this one. And this one are the scalar analysis. I forgot to mention it, the scalar variable. There is a flag that we use in the scalar mixing analysis. It's called water age on. This one, it's like it gives you an idea on the regions where you have stagnation, fluid stagnation, and which regions are free flowing. For example, in here we have the inflow of our methane and water. And you can see how in here we have only the water age is about from 0 to 10 hours, and in this region it's like stagnating. And for more information about this flag, I would recommend that you visit this this link. So now let's move to the transient simulation. Here, the model, I have changed it in a way that I have one inlet and one outlet, because I'm going to it's just having a very simpler model that I wanted to run transiently. So for the inlet, it's as usual mass flow rate and scalar one, the methane. And initially, I have inside the tank water. So initially, we have water, and then we're gonna pump in methane. And for the outlet, we have pressure. So as I told you, scalar 0 is initially set for the fluid volume, and scalar 1 is for the inlet. For the meshing is like the steady state analysis, suppressing the solid parts and using refined mesh over the interesting areas. And then for the solver settings, we're gonna set the transient simulation, and we're gonna add a time step. I would suggest, or I would recommend, to start by a time step equal to 0.5 and with 3 inner iterations. Here I recorded the scalar variation for 200 seconds, so you can see the results of the simulation. I didn't complete the simulation till the end because it needs more time to do it, as the dimension of the tank is very big. So over time, you will get the water mixed with methane, and it's gonna flows out here as its density is big. So probably if I let the simulation run for a longer time, we will get here only methane, and water will be evacuated completely. So what do you have, Marwan, right now?
No, that's very interesting. Unless maybe there's a dead spot in the tank where it's going to have water staying there, but probably eventually it'll all flush out. So
yeah, exactly.
It's basically a mixing / flushing out analysis. If you wanted to do just purely mixing, you would need to also have an inlet for the water so that they keep mixing together, and you will never have all the water flush out of the tank.
Right, this is it.
Yeah.
So I think you said that you imagined like a third model. Did you say?
Yeah, you mean for the tank or
no,
for the
another
presentation?
model.
Yeah, sure. If you can make me the presenter here, I can share my screen, or I can make myself the presenter. And all right, let me know if you can see my screen now.
Yeah, I can see it.
All right. So what I have here is another scalar mixing analysis, and this model here is basically of a building. This big volume here is air. If I suppress or hide that, we have, let's say, an industrial building where we have 16 stacks where some gas is going to be emitted. Let's say it has a foul odor, and we have the ventilation inlets on this side, those 5 inlets, and you want to see how much of that gas recirculates back into the inlet. It's a simplified model, of course, but the purpose is to show the basic steps and how you would do something like that. So what I have here, this part here, we're going to set that to solid, maybe concrete. It doesn't really matter because we're going to suppress it actually. And this here is going to be, I'm going to edit that. It's a fluid, it's air. Actually, I'm going to pick it up from my material library. Let's not do that right now. Let's just go in and make it ourselves. So this is going to be an air material properties, and the density is going to be a function of scalar. So I'm going to click on density, change that from equation of state to, actually, I need to set that to variable first of all. And then I'm going to go in and edit that, change maybe that to my material, and click on density and make that piecewise linear and make that a function of scalar. And let's say at the scalar 0 it's going to be 0.00. Actually, that's kilogram per meter cubed, I think. 001855 at scalar 0 and 0.001455 at scalar equal 1. Now, the exact numbers are not crucial, but of course in your actual model you want to be as accurate as possible. Let's save that. Oops. And apply and hit OK and apply. So here what we're going to have to set that up, we're going to select all these outlets here. And we're going to have a certain volumetric flow rate coming out. Of course, we're going to reverse the normal here, and and let's say feet cube per, not velocity, volume flow rate, feet cube per minute, and let's say 3600, and apply, and then I'm gonna select that here and edit it and make that a scalar of 1. I'm gonna go to the inlet to the building here. So we're not modeling the air inside the building, actually. We just want to see what comes in at these inlets. So we're gonna set a volumetric flow rate here of 11,520, also feet cube per minute. And we're not going to say anything about the scalar here because we want the program to calculate the scalar for us, and we're going to then show the air and apply some conditions on this. So let's say we have air coming in here at 5 miles per hour. So the idea here is to see how the inlet velocity of the air, the wind basically, how that's going to change what goes into the building. So if the wind, if you have high wind, high velocity wind, it might drive all that air coming out of the chimneys away, and not much of it is going to re-enter the building. If we have a slow velocity of the wind here, you might have recirculation, and the air with the odor will come back into the building. So the idea is to study that. So we're going to apply that velocity here, and the scalar also here is going to be 0 because this is fresh air, and the scalar is going to be, 0, left at 0. So scalar 0 coming in here, scalar 1 coming out of the stacks, and we're going to set the pressure equal to 0 on the back end. So that's going to be our outlet. It doesn't matter what units it is. Let's say PSI. And we're going to have slip or no slip symmetry on these 3 surfaces over here. In the solve dialog, we're going to go to solution control and set that to ADV5. And we're going to go to physics, advanced, general scalar, and we're going to set this to 0.15 for the diffusion coefficient. And I actually had it run for 500 iterations. It converges in less than that. And we will go ahead and solve that. Of course, we're not going to do that right now. I already have that solved, so I will bring up the already solved design here. And what I did is I made a few different conditions here: 5 miles an hour, 1 mile an hour, 3 and 10 miles per hour air coming in from here to compare them. And sometimes you get results that you don't really expect too much. So if I go to the decision center and I look, I'm displaying, I put 2 slice planes here, and I'm looking at the scalar. So if I go back to results for one of them, I define those 2 slice planes, and under scalar, I actually change the legend to just the maximum of 0.25 to see it more pronounced here. Otherwise, it didn't look too pronounced. So if I go back to the decision center and compare, this is my 10 miles an hour air. Let's go to the next one. Actually, we can change it here. This is 5 miles an hour. You can see the difference. When the air velocity is quite low, 1 mile an hour, Probably our bounding box here is not large enough because you can see it being basically chopped off the top here. The air wants to go up higher, so probably what comes in here is not going to be a very accurate representation. And this is 3 miles an hour. This is probably the box of air, outside air, is big enough to model 3 miles an hour wind. But I think the 1 mile per hour wind is not too representative because a lot of it is going to want to go up further. And what we want to look at here, back in results, if I select this plane here and go to the bulk calculator and look at the scalar at that plane. So that plane is the, let me just close that here real quick. It doesn't want to zoom in for some reason, my mouse. But anyway, that's the inlet plane to the building, basically. That's this plane here. Oops.
Marwan, you can go to the view and zoom in manually, not using the mouse. Probably it will.
Yeah.
True. Work.
Yeah, but it's not. But it's not allowing me to select the plane that I want. Let's remove this plane. We don't want to remove all. All right, that is being a bit.
Oh yeah.
Yeah.
You're running a lot of analysis.
Yeah, I think so. But the idea is to go here and go to bulk, which, well, let's change the scenario here. Maybe it'll work. Okay, it's working now. And if I go to bulk and I calculate the scalar, on that plane I have basically 6 areas, the big area here and the 5 inlets. Of course you can tell which is which just by the sheer magnitude of the area here, so we're not going to look at this one, we're going to look at these, and this tells us what the scalar coming into that building is at each one of those inlets. An average maybe of 0.03, which might be a bit too much. So perhaps when the air velocity is slow, you're going to get more circulation. When the air velocity is high, let's look at 10 miles an hour. Results, we'll pick planes. We will pick this plane and look at the bulk and calculate the scalar. It's 0.02. So you will get more or less depending on the inlet air velocity, and then you can decide whether your stacks maybe should be higher, whether your air inlets should be on a different side of the building, and so on. So this really helps you determine whether you have a good design here or a not so good design. And if people are complaining that they can smell the odor from the stacks, then you can change the or think about that. That's probably not going to be cheap, but it has to be something that needs to be done. It's probably easier to make the stacks higher than it is to change the location of the air intake to the building. So that's one example where we are looking at the mixing and looking at the results of the scalar and determining whether we have an acceptable situation or something that needs to be changed. In this case, again, just to reiterate, the material properties, only the density was a function of scalar. You can also have the viscosity as a function of scalar and any of the other properties that we see over here as a function of scalar. By editing, you go to edit and you can say viscosity again instead of constant. You can make that piecewise linear. Where's that? Or where is that? It's down here. and make it as a function of scalar. And the fact that the density is a function of scalar, that doesn't mean that viscosity has to be a function of scalar. Viscosity can actually be a function of temperature if you wanted it to be. You have total control over what your properties are a function of.
In Marwan, we have also to make sure that our air material is variable in order to allow the fluid properties to vary.
Sure, yeah. And don't, of course, don't go with that variable here, because that's the name I gave it. You want to look, you want to look at what's in the brackets here. Actually, maybe that's, again.
Probably you changed the materials or the settings after running the simulation.
That's right. That's right. But that's good. That you bring up a very good point. You always want to pay attention to that.
And exactly. This is very important.
Yeah, otherwise you're not going to get what you are looking for. Because really the scalar, the scalar is two things. If the material property is set to fixed, like we said earlier, you can still do a scalar analysis and see and basically track one fluid relative to the general domain. That's perfectly an acceptable use for the scalar, but also in many cases the properties are a function of that scalar, so you want to make sure that you set that to variable and run the model like that.
So the properties can vary according to the scalar.
That's right, because it's not enough to define the variable properties like I did. You also want to make sure that you use them as variable by checking this this radio button here, because just defining them as variable is not enough. You also want to say, I want to use that variable properties to see that difference. So let's say the density in this case changes quite a bit. The air coming out of those stacks is very heavy. Then it's going to be more of a chance for it to come down and go into the inlet. Whereas if it's light, it might not present as big a problem for it coming back into the building. Very good point, Amal. Thanks.
You're welcome. It was very interesting.
Yeah. So, and sometimes, like I said, you might discover that things are not intuitive. The results are not intuitive, and sometimes you might discover that that air domain that I have here might not be high enough, or maybe even though it's not high enough, the results might still tell you what you want to know, without it being as high as it needs to be.
Yeah, exactly, to have an idea of your end goal of the simulation you're running.
Yeah.
Or even sometimes you don't have like an idea about how should be the size of the air domain. So when running the simulation, you're gonna say, okay, so this is preventing a good circulation of the flow. So let's make it bigger.
That's right, because the fact that I have a bounding surface basically on the top of the slip symmetry condition is it's gonna keep the air down and maybe force it to go recirculate into the building, whereas in real life, if it had more volume, it's gonna go way up and not actually be forced back into the building. So you want to pay attention about that. And so just looking at the velocity actually might tell you that, but also looking at the scalar is helpful to see how it's being, artificially kept down closer to the roof of the building, whereas in real life, at a slow wind velocity, it might actually go way up and not be circulating back into the building.
Yeah.
Do we have any questions?
I think it's now time for questions.
Yeah.
You can ask wherever you want. We tried to have different models with different settings in order to cover the maximum that we can get or that we can present for you.
Let's see, do we have any questions here? Okay, someone was asking what the website where Amal grabbed the faucet. It's called GrabCAD. GRABCAD, GrabCAD. And anyone can use that. And I think you have to sign up to be able to download the models, and you can do a search what you're looking for, and even the CAD format if you strictly want Inventor model or a SolidWorks model or Pro-E model. You can also filter by the CAD package you want it to be in. And some of the models are not very clean for something like an FEA analysis, but some of them are, and some of them, even if they're not clean, they can be cleaned up pretty easily. But it's a very good resource, actually.
Exactly. Even for the water tap, for example, I had to clean it up because there is a lot of details that I'm not interested in simulating my fluid flow. So I made it as simply as possible. But it still doesn't have a mixer inside it to regulate the mixing of the two fluids or of the two temperature water.
Yeah, I think the faucet in our tutorial that has a mixing device inside of it that will cause a more uniform temperature to come out of the faucet. So obviously the example that Amal did, if you were to put your hands under that faucet, you would feel the difference. You would feel both hot and cold water and not just uniform temperature water. So, it probably, practically it won't make a difference, but as far as comfort, yeah, you don't want that. You want to feel a uniform temperature on your hands.
Yeah, exactly. That's why they get rid of it, of this old-fashioned tap.
Yeah, or the separate taps.
Yeah, exactly.
Yeah, and yeah, the mixing tank was also an interesting model. Let me see, do we have more questions? Oh, there's a bunch. Okay, let me see.
So someone here is asking, can you show scalar effect for the tank? Yeah, sure. It was on the presentation, but I still can show it in here.
Yeah, do you want to make yourself the presenter and show us that, Amal?
Yeah. So I'm going to make myself a presenter. This one. So let me know if you see it, Marwan.
Yeah, I do see the model.
Okay. So here we have the result of the scalar variable. I can make it shaded, and here how the scalar variable look like. And as I already showed you the results of the transient simulation, I saved the results for each 20 time step, or 10. So here's it. For 200 seconds. Yeah.
All right. Another question was, were these models run as turbulent or laminar? I believe they were run as turbulent. I know mine was run as turbulent.
Yeah, all mines also were run as turbulent models, because we have a change in velocity, and we have like turbulent flow inside our models.
And there was another question about mixing, water with steam with water. As a general rule for doing these scalar and mixing analyses, you want the viscosity of the two mixing fluids to be close to each other. You don't want them to be way different. That's basically the rule of thumb that you want to use. So if you're using, let's say, oil and water, I'm not sure if I would want to do that. Because the viscosity is quite different. And remember, they are defined as one fluid to begin with.
Okay, there is here a question saying, is it possible to have more than one scalar? I'm not sure that I understand the question, but
is it possible to have more than one color?
One scalar.
Oh, one scalar. I mean, yeah, you can have something coming in at, let's say, 0.5. It doesn't have to be 0 or 1. It's not a binary choice. Yeah.
Marwan, I think for the scalar boundary conditions features we only simulate two fluids. That means 0 and 1, not more.
I was thinking a mixture of the two coming in, say, from another element.
Yeah. Yeah. We define scalar 0 and scalar 1.
Okay.
Exactly. So if you're mixing, for example, 3 different cases, you have to see your density. Is it changing according to pressure, to temperature, or is it changing according to the equation of state? So it depends. And then you have to calculate your density and gas constant for your mixture. It should be made manually, actually.
Okay, good point. Any other questions came in?
Okay. To model the effects of density, variation, buoyancy, do you only need to enable gravity and give it a direction?
I believe you do.
I am not sure, but in my case, I didn't define gravity. I think it's important to define it when you're studying heat transfer. But for only the flow, the fluid flow, or the mixing flow, you don't need to define gravity.
That's right. It doesn't give you that option, actually, unless you click on heat transfer, and that's when you get the gravity.
Yeah, exactly.
Yep.
So it's not important to define gravity as long as you're studying the fluid flow, not heat transfer.
So actually, it would be interesting to check the heat transfer and activate gravity, because that will, that's probably will make a difference on it. Let's say in my example, even though I'm not introducing temperature as a variable in my model, that would be the only way to get the gravity, so that we set the direction for the gravity. Otherwise, if it doesn't know the direction of the gravity, it wouldn't use the gravity. It has to know the direction of the gravity.
Okay, good. So, do you have other questions so we can help you to answer them? Or probably you can reach out to us whenever you want.
Yeah, if we don't have any other questions, yeah, if you think of anyone who has questions, they can send in a tech support case, and we'll be happy to answer that.
Marwan, we have here a new question. Can we simulate a narrator high pressure steam air versus air, or yeah, for mixing or moving water?
Like I said earlier, when we have steam and air, the viscosity is going to be quite different, and I probably wouldn't want to do that in an analysis like that. They're not going to be mixing together. Because of the viscosity.
I think it's an interesting topic. We can for the ones who ask about the steam and air, we can reach out to them for more detailed information.
Yeah, I think there's an article in the knowledge base that deals with that question specifically. Not those two materials, but the case where you have two materials with quite different viscosities.
Mm-hmm. Yeah, that would be good, Marwan. So.
And we're going to make the presentation available and the models available actually a little later on.
And under the link that we shared.
On the first slide, there was a link, and the models will be available in that link.
Yeah, and the YouTube video should be available by tomorrow. So, any other questions?
If not, then thank you everyone for joining us, and I hope that was informative. And we look forward to hearing from you if you have further questions. And anything else, Amal?
Yeah, thank you everyone for even participating with your questions. It adds more values to the information we added. Thank you very much for attending our webinar. And let's see what we're gonna deal with for the next part of our mixing analysis. So these information that we provided, it's like basics or best practices to have or to run scalar mixing analysis. For the second part, we're gonna deal with more complex simulation. So thanks again, and have a nice day or evening.